talking on a project that's joint work with David Pennies and Noah Snyder that we've been working on since like December 2019, if you can remember back that far, and really hoping to have this out the door soon. So look for this on the archive in the very near future. The story I'm going to tell you today is a little bit historical. So I'm going to start, and it's also sort of personal. So this is the order in which I learned this material. And so I'm going to start with telling you about the subfactor side of the story and turn that into something planar algebraic and then tensor categorical. And throughout this, there's this theme of these things called connections that allow you to construct a certain kind of subfactor that we're trying to interpret in, well, eventually in the tensor category setting, understand sort of this condition that sort of at first looked like this slightly gibberish combinatorics, kind of trying to understand like what that's saying in a more systematic way. And this is a great example of something that happens a lot to me in math, where you learn some idea and then you transport it to a new setting in a hope that your life will be easier in this new place. And instead, you're like playing whack-a-mole with the difficulties. Like they hide, but then they pop up somewhere else. And so the thing I'm telling you, unfortunately, is not a sort of story where we started with this thing that was very mysterious and then we got an answer that made it all sensible and easy to follow. It's not that kind of story, just to give away the punchline, maybe. Okay, now I'm going to have to ask you to give me a certain black box when it comes to some operator algebra stuff. So the things that I study are called subfactors, and the way that I study them is very algebraic, but under the hood is some analysis, okay? And I already have too many definitions in this talk, as you will see, so I didn't want to really start at zero. So the thing that I'm asking you to do is accept that there's something called a von Neumann algebra, okay? And more than just accepting that these things exist, except that they are perhaps interesting. People have wanted to study these for many decades. Now, what you could think about is something that generalizes, say, a matrix algebra, okay? Instead of working over a finite vector space, our vector spaces are infinite, but they have, this is not just bounded operators on the Hilbert space. These are something perhaps more they have more nice properties than just that, okay? And those nice properties, like I said, are analytic or topological, and that's exactly what I'm not going to be talking about. But there's a theorem in von Neumann algebras that says that a von Neumann algebra is a direct integral of factors, which are things with trivial centers, right? So in finite dimensions, you have, multi-matrix algebras, things that you add up a bunch of matrix algebras and you get that. And that's really a really good analogy for these von Neumann algebras we're dealing with. If you understand the factors, which have trivial center, then you have a chance of understanding the whole thing. Okay, so if we have two factors, one is contained inside the other, then we call that a subfactor, okay? And now we can talk about the size of the inclusion. We can talk about how big our larger factor B is by looking at its dimension as an A bimodule. So, okay, for example, this is the real black box in this talk, this hyperfinite 2-1 factor, okay? And it's a limit of finite dimensional things with a certain closure. But what's nice about it is that any finite group has an outer action on this, and also that it is unique, that anything that you construct as a limit in this way is the hyperfinite 2-1 factor. So it's kind of the unique small things, and all your groups act on it. And so we can import a lot of classical algebra to this setting by letting a group act on our hyperfinite 2-1 factor. For instance, we can take a cross product construction. Now our subfactor really just reflects the structure of the group G. So for one thing, if you look at the size of the inclusion, it's the size of the group. And if we took a subgroup H and we did this cross product construction, then the index of our subfactor would be the index of the subgroup. Okay, and so far you're saying, yes, great, this all mirrors stuff that happens for finite groups very nicely. And the twist is that there's a lot more going on here. So the famous theorem in subfactor theory from 40 years or so ago by von Jones is that the possible indices for a subfactor can be either from a discrete series, if they're less than 4, they can be of the form 4 cosine pi over n squared, or can be any real number between 4 and infinity. And so even though this thing is a dimension, we call it an index, it doesn't have to be integral, okay? And so it's already a clue that maybe there's something going on here that's different than analogies with finite dimensions might lead us to expect. Oh, wait, no, I have a clicker. Okay, the index is the first invariant for subfactors, but as you might expect with these things that are big and infinite, we would really like to have more invariants. It's easier to get your hands on the invariants than the things themselves. And so there's 2 more of these common invariants. One is called the standard invariant, and the other is called the principal graph. Okay, and the standard invariant is a kind of big one that encodes a lot of the representation theory of your inclusion, right? So remember that we had A was a subfactor of B, and if we look at bimodules generated by B, considered as an AB subfactor, we can take this and take its dual, and I'm sweeping under the rug here the fact that this tensor product that behaves exactly the way you would expect is very hard to construct. But we're allowed to tensor these together if the indices match up. And basically, we can start fitting these together, build up bigger and bigger things, and we can look at the irreducible bimodules that are contained inside one of these powers. Okay, now this is some sort of algebraic gadget. In a few minutes, I'll tell you it's a planar algebra, and then later I'll tell you it's a tensor category. But the first people to study subfactors didn't sort of have this language, and so they created various things like the lambda lattice, the paragroup, to sort of reflect that there was this algebraic structure here, but it was a little bit unfamiliar. I'm not going to go deep into any of those because, like I said, I'm already planning on telling you 2 different ways to think about this. Yes?
The example is easy way to describe an example of a non-integer dimension.
I don't have an easy non-integer example. I can tell you about some non-integer examples, but you'll have to wait a few slides. Okay? Okay, so we have the index, which is a number, and we have the standard invariant, which is a big collection, some sort of algebraic data. And in between these 2 is the principal graph. Okay, and so this is a graph that represents kind of the tensor structure of these things. So you take a vertex for every irreducible bimodule that shows up somewhere here, and you connect 2 of them. If when you tensor, what did I say here? When you tensor y with x, you get a copy of z showing up. Okay, and now we have a nice dual structure here for Frobenius reciprocity, meaning that this is a symmetric relation. Okay, shouldn't be obvious, but it is true. And so therefore, this is not an oriented graph, but an unoriented graph. Okay, and then because what I've described here is a relation between AA and AB bimodules, we'll also have the same data if we look at, say, BB and BA bimodules. And so there are sort of 2 graphs showing up. So in the original literature, people called this the principal graph and the dual principal graph. And nowadays, you're more likely to hear just the principal graphs, plural, because there's no sort of thing that's more natural about one of these than the other one. And I don't yet have a non-integer example, but I have another integer example here. Okay, so we're going to go back to this example of the hyperfinite 2-1 factor with a finite group that acts on it. What if we take S3 as a subgroup of S4? Then all of our bimodules that show up in this standard invariant look like are tensored with an irreducible representation of H or of G. And if you look at the graph you get this way, then this is what you get. It's an induction restriction graph. And the principal graph is another induction restriction graph, but it's a little more subtle which two groups you take. Okay, so the index of this subgroup is 4. And this is, I think, what is this? This is E7, 1 of the extended Dinkin diagrams. So if you're in this case that we call finite depth, where you have a finite number of isomorphism classes of irreducible representations, then the Perron-Frobenius norm of your graph is going to be the square root of the index. And so in this nice setting, you can recover the index from the graph.
I'm a little confused about what's playing a role in R. R was some factor.
Yes.
Doesn't matter what R is.
R is the hyperfinite 2-1 factor, which I really am not going to tell you much about, right? So yeah, that's right. So here's
four. You don't really. It doesn't depend on R.
Yeah. So here's my black box, right? And R is definitely right. So this is called the hyperfinite 2-1 factor, and I really don't want to say more about it now, but you could ask me about it later if the details of this are interesting to you. Okay.
What about the other representation, S4? They don't occur in this graph? Or you just didn't drop them?
S4 has 5 symbols. Oh, is there one?
What? Yeah. Hold on. I thought that I had done this out carefully and that I had all of them. Okay, exercise to the reader. Okay,
Oh, sorry.
Yes.
so here, the question of which graphs can appear as principal graphs is interesting and extremely hard. Like there doesn't seem to be any like nice combinatorial way to think about it. So for instance, with the Dinkin diagrams, in which case we're in the index below 4 setting, we get some of them, okay? We get all of the A's. We only get the even D's and the even E's, okay? What does this mean? This means that there are subfactors subfactors that have these principal graphs, and these are the source of some of these non-integer index examples. But we don't get all of them. You can prove that there is no subfactor with principal graph D odd or E7. Okay? And then all of the extended Dinkin diagrams have at least one subfactor associated to them. Some of the extended ones have more than one. And I should say that I'm summarizing here, decades of very difficult work, as is the way in math talks. I'm going to like gloss over this briefly, but in fact, there was like, this is a lot of work that I'm hiding here. So this first one is due to a lot of people. I should probably mention Von Jones, Adrian Ocneanu, Kawahigashi, Izumi, and I'm sure I'm forgetting other people. And then the extended Dinkin diagrams is due to Serene Popa. And the next diagrams that we have appearing here are, this one is called the Hogerup principal graph, and this is the Aseda Hogerup principal graph, and this is the extended Hogerup principal graph. So Uffe Hogerup looked at some of this combinatorics about which graphs could be principal graphs, and he was able to rule a lot out. But he ended up with, just sort of based on combinatorial constraints, a few infinite families and then this singleton. And so over, many more decades, it was determined that in fact, the only things from his whole series that do exist are hover up, extend hover up, and essayed hover up. All right, and so what he was doing is he was looking at things with index just a little bit greater than 4. Okay, so the indices here are in the range between 4 and 4.5, I think. I could give you precise formulas for some of them, but
Does the little star over the leftmost node mean anything?
it does. So remember with these principal graphs, we were looking at the irreducible bimodules that showed up in some tensor product of B as an AB bimodule. So you have here, in this tensor category, you have a unit object, which is A as an AA bimodule. So that little star labels our unit. Okay, and if your principal graph is finite, then you only have finitely many irreducibles, and we call these kinds of factors finite depth. Okay, these are the ones that are easy to get our hands on. Okay, and so then, of course, the question is, how do we construct examples of these things, right? I mean, they're hard to understand. We have these invariants that help us, but we'd really like to be able to actually get our hands on some of these. And so we've already talked about how sometimes you can take algebraic structure you already know and leverage it to get some sort of subfactor algebraic structure. But the thing we talked about with groups is only going to give you things at integer indices. There's also constructions that make use of quantum groups, for instance. So there's ways to get there's ways to see more of the classical world here. The other thing that people did is take the subfactors we know and really sort of, shake them and see what else falls out. Like just get as much as we can out of the things we already have our hands on. And I'm not really going to be talking about this today, but one of the things that I've worked on is planar algebra constructions of subfactors. The thing I want to talk about today is sort of historically, after these first few steps, the next thing people did is looked for connections on potential principal graphs, looking at the sort of combinatorial data and trying to understand when there was an algebraic object associated with that combinatorial data. And so that's what I'm going to tell you more about now. Okay. And instead of telling you how to start with some numbers and get a subfactor, I'm going to tell you how to start with a subfactor and get some numbers out of it. Some of the rules those follow, and then leave it sort of sweep under the rug all the details of how we go the other way. So if you think about the principal graphs, it maybe makes more sense to think about this as a single 4-partite graph instead of 2 bipartite graphs, right? We have AA bimodules, we have AB bimodules, BA bimodules, and BB bimodules. And we can move between these in both directions, remember, but I've just put arrows here representing which kind of tensor with the generator we're doing to move. And this is a notation that I'll use throughout. So X, when I write X, I mean B as an AB bimodule. Okay. Now, are they what? By a joint. What does that mean?
Left and right.
Left and right adjoint. I don't know. Yeah.
You can put any cups or caps you want in your planar algebra, right?
Yes.
I think that says yes.
Okay, great. Okay, so if we had a loop around this graph, I claim that the subfactor structure lets us associate a number to that loop. And how do we do that? We think about this loop around the graph as a path from P to R that either goes through Q in the middle or it goes through S in the middle. Okay, and even though I haven't defined tensor categories, I'm going to draw really a tensor categorical diagram here, right? So we start with P and we're going to tensor with x on one side and x bar on the other side. And there's two different ways we could associate this. We could do this, and then this, or we could do it in the other order, like this, and end up here. And so each of these is a basis for the space of maps from x bar tensor P tensor X to R. One of them is right associated, one is left associated. Where do I want to write the different letters here? This one's a Q, and this one's an S. And since both of these are bases for the space, we can expand one in terms of the other, and the coefficient that appears is the thing we're calling the connection. Okay, so the connection is really just a change of basis matrix. Yes.
Sorry, this is something really silly, but I just want to double check.
Please.
This R is not the hydrofinite two.
Oh, yes, totally different R. Thank you.
Just double checking.
Yeah. Right, so now P and Q and S and R are bimodules that appear in my standard invariant, whatever those are. Yeah.
The sum over S.
Yes, this is the sum over S. Thank you. Okay, so we have a change of basis matrix, and it satisfies some conditions. Okay, well, the biunitary condition is really just saying that it's a unitary matrix. And then this second one is just sort of saying if we turn our head 90 degrees, it's still a unitary matrix. Okay, and I actually mean that about turning your head 90 degrees. Remember that we sort of picked a way to walk around this square, but that really we could take any path we want along the square. And so if instead of starting at P and ending at R, we started at Q and ended at S, what we get should still be a change of basis matrix. And so we need to have a second kind of unitarity. And this condition called renormalization, without the details of this aren't really important, but this says a similar thing about, the data coming from walking around the square in one way being connected to the data where you walk around the square starting at a different point. Okay, these are reasonably straightforward to calculate. And so the difficult condition is this one called flatness. Okay, and I'm going to put this up here. I don't expect it to be super illuminating because it wasn't the first time I looked at it. And part of the impetus for this project was like, I would really like to understand what this condition flatness is saying. Okay, so what you're supposed to do here is imagine that we've chosen bimodules Pi and Qi. And now this giant diagram built up of these little squares is supposed to be a sum over all the possible things we could put down in the interior of the square, and then take the product of the number associated to each tiny square. Okay, so, moral of the story, this is a giant calculation. If you're dealing with finite depth subfactors, so your principal graph is finite, then you have to check this for lengths up to twice the length of your graph. You have to be able to check this for vertices all the way out to the end. Okay, and so this is what I was telling you about at the beginning, this combinatorial condition that we'd really like to make more sense of and have a more systematic way to think about.
So the diagram we drew for the connection, was like for the F matrix.
Yeah, absolutely.
If you don't expect the invariant, but maybe, if you sum over some suitable combination of things, you can build invariants from those. Is that maybe analogous to this flatness condition?
Yeah, I'm not exactly sure, right? Because these are some particular subset of those elements of the F matrix, those 6J symbols, right? but you're always sort of pinning down two of these, right? You're not allowed to let the X and the X bars sort of range over the whole thing. So you're only looking at those. And what you're doing here is you're trying to use the fact that you're only looking at those to nevertheless get at some of the stuff deeper out in your category that you maybe have to take a lot of these tensor products to generate, right? And so, you know, yeah, I talked about the sort of whack-a-mole nature of the calculations here. You know, my suspicion is that we sort of get around having to check the pentagon equation in any detail by sort of zooming in on these particular things, but then at a cost of having to think about things like this.
So maybe just to clarify, so the connection, we described it as like combinatorial data associated with subfactor, but it's not an invariant, right? Like if I fix the QRF or should I think of it then?
So, you know, given a subfactor, we can take the principal graph, which is an invariant, and then the connection is like combinatorial data associated with the principal graph, and it's sort of, I'm not going to get into this, but it's usually sort of considered up to gauging. So there's notion of equivalence of connections, and so. Okay, great. Thank you. Okay, so this is the situation. My clicker has stopped working.
Usually if you click
On the computer?
not this computer is on.
Not this computer. Okay.
Not right? Oh, no, not working or not working?
No, not working.
Okay, then just use arrows.
I can use the arrows now? Great. Okay, thank you. So, okay, the theorem from Ocneanu is that this goes the other way. If we start with a pair of graphs and we have a connection, remember this combinatorial data that we're thinking of as like fitting together into some change of basis matrices, which satisfies the biunitary condition, the renormalization condition, and the flatness condition. If we have a connection that satisfies those, then we get a subfactor of the hyperfinite 2-1 factor with the principal graphs we started with. Okay, and so this is really like the strength of this approach, that we're able to get at these big, infinite, slippery things in this combinatorial way.
Does there need to be any consistency between the principal graph and the dual principal graph, or like?
Really good question. You are forced to have the same Frobenius-Perron eigenvalue for both graphs.
Okay.
But they certainly don't have to be the same graph. Now.
And just the way that's stated, right?
So remember that we were actually talking about this bipartite principal graph, right? And so really what we have is our principal graph, our dual principal graph, and then the same thing. So we really have both those graphs sitting in a bigger graph together.
Nice.
Cool. And so therefore they have to have also some vertices in common, which doesn't seem like a very strong condition, but still, like, they have the same odd vertices. Monica.
How, like, is there any injectivity theorem? Like, how many different subfactors do you get? Like, you just take a whole bunch of different graphs and all get the same subfactor?
No, because the subfactor you get has the principal graph you started with.
Okay, so
right?
change the graph. Yeah.
And so change the graph. Yes. Now, the interesting thing is that you can have a biunitary connection that's not flat. And from that, you will get some subfactor, and you don't know what you get. So if we don't have flatness, then we can still do this construction, but we don't know what we get as a result of it. But if we have flatness, we know that we end up with the principal graphs that we started with.
But do you know that every hyperfinite 2-1 subfactor comes from this construction applied to its principal graphs?
Yes, because starting from a subfactor, we can compute the connection just as these change of basis matrices.
And then you get the subfactor back if you run this.
As long as you started with a subfactor of the hyperfinite 2-1 factor, yes. Yeah.
Great.
Okay. Okay, great. So these ones, okay. So now I'm going to switch gears a little bit and tell you about planar algebras, which are going to give us a slightly more systematic way to think about connections and flatness. And so we start with pictures that look like this, where we have these inside circles are holes, okay? They're missing from the picture. And we have a single outside boundary. We have string that connects the boundaries of these things up without any crossings ever. And for reasons that we'll see in a minute, we also need a marked point around each of the boundaries. That's what these stars are. Okay, so basically what makes planar algebra is 2 dimensions of composition, which is to say that if we have a planar diagram where the outside number of points matches up with the inside number of points in a different diagram, we could pick this up and shrink it down and put it down inside here. And this is where the stars come in, right? If you didn't have the stars, you wouldn't know how to orient this after you'd shrunk it down. But with the stars, we know exactly how to put it here. And so we do that in this example, and we get this picture. And notice that part of our data now is a piece of string that doesn't touch any boundary, okay? This is not a hole, right? This is not an input. This is just a spaghetti-o, okay? A free-floating loop of string. Okay, so such planar diagrams form an operad, and we call a planar algebra something that has an action of this operad. So we have a family of vector spaces, and we think that all of these different circles on the inside are places where we can put in an input. And we should get a final output corresponding to whatever type of our output disk we get. Okay, so number of points along the boundary determines which vector space you're taking inputs from. Here we have V2 cross V5 cross V4, and we land in V7. And of course, composition of planar diagrams should correspond to composition of multilinear maps, right? This is what it means to say that we're taking a representation of the operad of planar diagrams. So here I've drawn one of the many, many things that you have to satisfy. And so, of course, if you're trying to create some sort of planar algebra from scratch, this is where all of the difficulty comes in, right? That this is a lot of conditions masquerading as just a single condition. Okay, but so this is not so bad if we take something that's already diagrammatic in nature. So I'm going to tell you now about the Temperley-Lieb algebra. Okay, so for this, basically it's like a planar algebra, but we have no input disks. So we connect up points on the boundary. A TLN diagram has 2 endpoints. So here are all the diagrams with 6 boundary points. And now we take those as a basis for a vector space, and we turn this into a planar algebra by literally taking your TL diagram and putting it down inside the input disk of your planar diagram. And once you've done that to all the input disks, what you have again is just information about how the boundary points connect on the outside disk. Almost. Now there's one thing that you could have happen here, which is that you might have something that looks like a perfectly reasonable TL diagram, but it's got some free-floating loops of string on the inside, right? We saw earlier how those can be created. And so the convention is that you just use a variable delta to represent those. You throw them away at a cost of, every time you throw one of them out, you multiply by delta. And so this is the same as delta squared times this picture. And now I've told you how a planar diagram acts on Temperley-Lieb basis elements. So just take the linear extension of that to the whole vector space. Okay, great. Here's an example. Okay, now the next example of a planar algebra is the standard invariant of a subfactor. Okay, so remember, this is the thing we get by starting with B as an AB bimodule and looking at all the bimodules it generates, either tensoring over A or tensoring over B. Okay, so in this case, our input vector spaces to the planar algebra are the invariant spaces of X tensored with itself n times. By this, I always mean X tensored its dual, tensor X tensored its dual. There should really be only one way to do this. Okay, and then the action of planar tangles is again coming over to this black box here, that there's a certain structure on subfactors of von Neumann algebras, things like inclusion, conditional expectation, multiplication, that have diagrammatic interpretations here, okay? And I'm still not getting into that. Things like that are just getting shoved under the rug here. And like I said, this is actually the difficulty in showing that something is really a planar algebra, but we don't need to talk about that. Wrong one. There we go. Okay, so what is flatness in the planar algebra context? Okay, so in the planar algebra context, you can think of, given a graph, you can think of any sort of loop. You can think of loops on that graph as being the basis of a planar algebra. And then a connection is a loop, right? A connection earlier assigned a number to a path that went around this four-partite graph. And so now we're saying a connection is some sort of four-box in my planar algebra that assigns a number to a path of length 4, to a loop of length 4 on this graph. Okay, and flatness in this context looks like saying that basically this connection can pull across an element, right? So here we have, if you like, you can just think of this as a string crossing some other strings, even though that's not planar. We just interpret those crossings as having a connection at these every time they cross. That's what we'll think of it as meaning. Now, this looks very different from earlier, right? But basically what this is saying is, in the earlier setting, we could have talked about flat elements, and the condition that our connection was flat was really saying that sort of everything was a flat element. And so here, we can talk about flat elements, and if your set of flat elements is big enough, you get back basically a subfactor. Okay, now my next few slides are about tensor categories, but I'm running low on time, and so I'm going to skip these. And I'm sorry, I don't really know what the people in the audience know, but I'm just going to assume that you know these because this is a representation theory conference. So tensor categories with a P. The P is for planar or pivotal, and it's silent. Okay, so you can still pronounce these. You still pronounce it tensor category, but it's just like every time you hear the word tensor category come out of my mouth, this is what I mean. Okay, that we have finite dimensional vector spaces for all of our Hom spaces, that our category is rigid and pivotal and Karubi complete. Okay. Again, if we look at bimodules for a subfactor, in this big setting, many of them form a tensor category. So all AA bimodules form a tensor category. All BB bimodules form a tensor category. And then the AB bimodules are a module category, or really a bimodule category, since both of these categories act on that. Okay. Temperley-Lieb-Jones is a tensor category that reflects really all of the structure of Temperley-Lieb. And I'm not going to say much about it. No, that's a lie. I'm going to tell you some things about it, that our objects are just points on a line. Our Helm spaces are connections in a strip between two lines, which again, we're not allowed to have them cross each other. And when we create a loop, we throw it out and multiply by delta. Composition is stacking, and tensor is concatenation. Okay, and we can also look at this, fix a set of vertices and look at all graphs on this set of vertices and turn that into a tensor category. I'm going to skip over the details of this so that I can get to my punchline, but we do have this structure. Okay, now an important thing to know about Temperley-Lieb-Jones category is that if you want to specify functor out of this, really, as long as you're working with P tensor categories, all you need to do is say where a single strand goes, and then all of the nice properties of a tensor category will tell you that you can, in fact, say where anything at all in Temperley-Lieb lands. Okay, and so in this context, the thing that we're calling a connection is a pair of functors from Temperley-Lieb-Jones into the graph category. And what you should think of is one of these tells you how to let your generators act on the right, and the other tells you how to let them act on the left. And now we need a commutator between those two actions. And really, this is kind of associativity data here, right? Saying that acting on the left and then acting on the right should be the same as acting on the right and then acting on the left. Okay. And so what does flatness mean in this tensor category setting? So here I'm going to just put up the definitions we've had so far. And interestingly, in the tensor category setting, the definition of flatness looks really different. So what's going on in this picture is that we start with a bimodule category, and we want to know if we can promote it to be a tensor category in a way that's compatible with the actions that we already had. Okay? And so when does that happen? So if we're given M, which is our semi-simple bimodule category, and some particular element, little m, and we want to make that the unit of our tensor structure, how would we put that structure on M? Okay, so all of this horribleness is just saying that Temperley-Lieb acts on M on the left and on the right, and those two actions commute with each other. So that is this arrow from here to here, and we take its dominant image, and that's where L comes from. And of course, endomorphisms of M that commute with the right action of Temperley-Lieb-Jones embeds into endomorphisms of M. And then at the bottom here, we have just M itself, right? And first of all, the Temperley-Lieb-Jones elements can just act on an element of M. Or if we go all the way over here, we can evaluate our endomorphism at M. And of course, we should get the same thing for doing all of these. And so if we zoom in on this little triangle here, TLJ, L, and M, then if the map from L to M is full, we have a splitting that goes in the other direction. We can go from M back up to L. And then if L and M are equivalent, then we can take the tensor structure of L, which as a subset of as a subcategory of the endomorphism category has a tensor structure of its own, and import that to M. Okay, and so if this map is full, then we know that M is in fact a tensor category. And so this is what it means to be flat in the categorical framework. All right. The end.
Very much. Are there any questions? So, I mean, I have a big recollection of, talks from a long time ago that, constructing, for example, these like extended O's and these guys was really beastly computation. Does flatness like actually make that easier?
No, like I said, whack-a-mole on difficulty.
Conservation of trouble.
Conservation of trouble. Yeah, I mean, to be fair, I have not yet tried to use this approach on anything that complicated, but just doing it for the, simpler ones that have been known how to be constructed for a long time, it is just as difficult as you would expect it in any other context.
Right, and then I remember some discussion of having to like find simultaneous solutions of like thousands of quadratic equations. No, okay.
No. The planar algebraic construction of subfactors, which Ben is talking about, was all basically linear algebra, right? There were 10,000 by 10,000 sparse matrices, but linear equations, much less horrifying than quadratic equations.
There was something about that.
There were 19 quadratic equations, I believe.
I mean, it seemed like 1,000.
There were quadratic equations on a vector space of size, on an algebra of dimension 10,000, but.
So just to be clear, this TLJ, M, and L are all categories, right?
Yes, Temperley-Lieb-Jones is a category. M is it starts out as a semi-simple bimodule category, and we want to know if we can import a tensor category structure onto it.
Yeah. And so in this case, the splitting that you get, is it an adjoint? Is there a reason you drew it on the left?
That's a good question that I don't have the answer to.
Okay.
I mean, the short answer is I drew it on the left because I had to put it somewhere. I don't know.
Yeah. Well, if nothing else, every equivalence can be improved to an adjoint equivalence. So you could make it an adjoint if you wanted to, but you might have to twiddle things to make that work. But if so, there's some machinery of monadic descent that fits into exactly this kind of picture that might be relevant.
I would love to get some more details from you about that. Excellent. Okay. What else?
And so this conditional expectation, is it like a map from B to A?
Yeah, exactly. Exactly. Right. So we have A contained in B, and part of being subfactors is that we can get a conditional expectation from B back down to A, which respects, the action of things.
So that's just part of the data being and stuff.
That's right. That comes for free with a subfactor.
And I had a less precise question. Do people look at not planar algebras, but with higher genus surfaces?
I think you would call that a skein algebra, and people definitely look at those, but they don't have application to subfactors, so I don't know about them.
Are there any more questions? But it's not that.